And let me share my screen. Please let me know when you can see my screen.
Yeah, we can see it.
Okay. The first question is the binary tree Inorder traversal. So basically, we have to return the Inorder pattern of the tree. And before this, so I think most of the people should be aware of Inorder, pre-order, post-order, correct? So basically, we have to just return the Inorder pattern of the tree in a list. So if I have to so if I have something like, so this is, can you see my whiteboard?
Yeah.
So if I have something like 1, then 2, and 3, and then 4, and then let's say 6. So what should I have to return back? So what should be the answer? If I have to do in order, so in order is
Left root and right, right?
yes, visit left, visit node, and then
तेरा ऑडियो है
visit right.
ऑडियो है
Okay, so this is pre-order technically. Right?
बोलो ऑर्डर आया
If because they're not participating, they can. Shashank, can you mute someone? Okay, I think we're good now. Okay, so what should be the answer here? So based on this, so answer should be 4, 2, 1, 3, and 6. Correct? And if I would have something like here, anything like 5, then the answer should be, I just need to put 5 over here. That's it. Oh, sorry, the 5 should be here. Okay. Is it clear?
Yes.
Yes.
Yeah.
So here they have asked that we should not be if I have to do a recursion, this would be really simple. But if you see in the question like recursive solution could be trivial, and we do iteratively. Recursion is really simple. I can just pass a list when I'm visiting the node. I can just put it in a result list.
Hey, your voice is breaking.
Is it better now?
And can everybody else mute their speakers
Yeah. If you are
and microphone as well? Yeah.
Okay, so Asim, this will not be in order?
This will be in order, but I'm telling the recursive solution would be really simple. And as part of the question, they told like as a follow-up, can you do iteratively? So
Because I got confused that you on top you mentioned pre-order.
Oh, yeah, sorry. My bad. This is in order.
Okay, cool.
Okay, so so if you guys are comfortable with a recursive solution, we can think about iterative. That would be tricky, but if people want me to talk about recursive, we can even do that first.
No, let's go ahead with iterative itself.
Yeah. So if you have any question on recursive, you can talk. But recursive would be really simple, like how you do in order while doing in visiting the node. Just put it in a list or something. That's it. So let's talk about a recursive solution. How I can do a recursive solution? Anybody has any idea?
I think we can maintain a stack.
Yeah, stack.
That's what, yeah.
And then there is something like Morris Traversal, which does not take a stack at all.
Yeah.
So let's talk about the stack solution. So if I have to do a stack solution, what should I need? Let's put something. So if I have to do a stack solution, I have to find a way to come back. That's why I think we are leaning towards a stack solution. So if I'm going from 1 to 2 to 4, yeah, 4 should be go to my result class, but I need a way to come back to 2 and to go towards 10.
Yeah. Yeah. I think we need a stack because we wanted to trace back to the parent.
Yes. And so if I just create a stack and what I need, so if I put initially if I put 1 and then I put 2 and then I put 3. Oh, sorry, there is no 3. And then 4. So initially I need to build my stack till 1 to 4, and after that first answer would be 4. I can remove this from my stack, and now from 4 4 does not have a left and right. I can remove another element from stack, which is 2, and put it in my answer list. But 2 has a right, and we want to go, so next thing should be 11 in the answer. So we have to go towards its right and then still go towards its left. So then I'll put 10 in my stack and then 11. And after that, I can remove the top element. So after 11, there is no left and right. Otherwise, I should have gone till left more. Let's say if there is something like 12 here, I should have gone more in terms of that 12. Then I could have removed 12 from my stack and put it in my answer list. And after that, the top element will become 11. 11 does not have a right, so 11 can also come. And then 10 does not have a right. 10 will come in, but it does not have a right. We don't need to do anything. After that, we'll get 1. From 1, it has a, I can remove 1, put it in my result, but 1 has a right. So I have to go towards it right and go towards left of it. So basically I'll put 3 here and then 5. So 5 is the top element in the stack. I can put 5 here, remove it from here. 5 does not have a right. From then 3 can be removed, and 3 does not, 3 has a right. So I'll put 6 in the stack. And now the top element is 6. I can remove it and put it here. And then that's how I got my traversal. So the trick here is we have to go towards left and start removing elements. If somebody has a right, put that in the stack again, and then again go towards its left branch and put everything back in the stack. Is that clear?
Yeah.
Any questions on that? I can answer. If that is clear, then I can probably show the code.
Yes, let's go with code.
So I took a stack. Initially, what I did, I took the root, passed to my stack, and start going towards its left, like I mentioned, till I can find a left. I went till there. In the previous example, it was which I showed on the whiteboard. It was like 1, 2, 4, and then I stopped. Then after that, then the things which are in my stack is 1 to 4. Then after that, I removed 4, and let's say this is my result. And in my result, I have put 4 there. And if 4 has a write, simply I'm passing 4's right to again the update stack and putting that in the stack, and then again go towards its left. So in that way, this traversal will work.
So the worst case, in this case, the stack will be of height 10, right? If it is left skewed or right skewed.
If it is left skewed, the stack would be like have everything in the stack.
Yeah. Yeah, it's fine.
So is it valid to say at any time the stack only contain the left subtree, node from the left on the left subtree?
Yeah, going left. How much left we can go?
Even like if we go right, then we still go left, right? So
Yeah. So at any point initially it will be 1, 4, 3 in the stack. And again, if we find something on the right and go towards left, then that would be the maximum elements in the stack.
yeah, but my point is that contain like the left view of the tree?
Not exactly. If let's say we have five should have. See, this works. I think one more. And one. Okay. So left side of what is the left side view of the tree? 1, 4, 3, 5, right?
Yeah.
But initially in the stack, I will only put 1, 4, 3. This is the only left I can go. When I'll remove 3, then I'll go towards its right.
Yeah.
Basically, how left I can go, that would be in my tree. And then after that, I'll see if there is a right. And then again, put all its left in the stack.
Yeah, so that by the end of that, we might see only the left view of the tree, right? Because we go 1, 4, 3, it's a left view of the tree, and then we go to 5, it's also a left view of this tree.
No, but by that time, 3 is gone from the stack. As soon as before I put 5, I have already removed 3. So in my stack, so initially what is in my stack? 1, 4, 3. Then I have removed 3 and put 5. then initially 5 will also go on. And then I'll remove 4, then I'll remove 1, and then I'll put 2, and then 2 is also gone. So at any point, it could be like all its entire left view is there, but it depends how we are saying what is a left side view of my tree. It might be as big go, we can say yes, left view of the tree.
Okay, yeah.
And I've seen like there are sometimes a follow-up question like, hey, if you can't take extra memory, what should you do? So for that, there is a particular algorithm, Morris Traversal. If you guys are interested, we can talk. Otherwise, we can move to the next question.
No, we should. I think we should talk about that. Yeah.
Okay. So, so if you have seen the stack thing, why we have used a stack? Because we need a way to come back, right? So if you see this stack solution, we took this stack solution because we need a way to come back. Otherwise, otherwise there's no way. Like when I've printed 4 here, if I don't know to come back to 2, how I will able to proceed with 2? Correct?
Yeah, that's true.
So so if I know a way to come back to my parent, then I don't need a stack. So what Morris Traversal algorithm says that find the predecessor and link it back to the parent node. So for example, here, what I will do for 1, what is the predecessor in this? If I have to do in order. So let's also write in order for that. So its in order is 5, 4, 2, 10, 1, 5, 3, 6, correct? So if I first what I have to do, I have to find the predecessor of whatever current node I'm visiting, and I need to so if I'm able to find the predecessor, I need to just link it with this guy back. And the same way, what I'll do when I'll go to 2, what is my predecessor? For 2, the predecessor is 4. I'll link it this back to this guy. And when I'll go for 4, what is my predecessor? It is 5. So I'll link it back. And after that, if I couldn't, after that, now I have a situation where from 5, I can't go towards left. So I can print 5. And from there, if I have to go towards its right, but if what I have found like from right, again I go towards 4. From 4, again I come towards 5, and I find like 4 exists on the right side of 5. That means I have already done this step. The first time I've linked, second time I found 4 is on the right side of 5. So that means I have done with this guy. So what I can do is I can remove this link and print 4 here. So same from 4, I will go towards its right, which is 2. From 2 again, I'll come back to 4 and find, okay, the right side of 4 is myself only, which is 2. And I can remove this link and print 2 here. So from 2, again, I can go towards its right, which is 10. And from 10, if you see there is no left, I can print 10. from 10, I will go towards 1, which is right.
Wait, why 1? I thought like we gonna point to the parent, but this one we point to the grandparent.
So basically, I have put 1 as the right child of 10. If you see, there was no right child of 10. I just linked 10 and 1 as a right child.
But before, when we was at 5, we point to 4, right?
Yeah, that was a that was
That's
a
the
link.
parent.
No, that was the link I have. So I found what is the predecessor of 4, which was 5, and I made a right child of 5 as 4. That was in my first step. When again I'm coming back from 4 to find, I found that this thing I've already done. So this time I just removed that link.
But like look like 5, you point to the parent with a 4, and 4 you point to the parent is 2.
No,
But with 10 we point to the grandparent.
There is nothing like a parent or grandparent here.
Oh.
It's just a predecessor. So let's do it one more time. I know this is confusing.
Does it happen to all the right children, rightmost?
When you say most, rightmost.
Yeah, here this is 10, right? So that's why it points to 1.
No. So it's just a predecessor. So for example, right now, what is my current node, from where I'm starting? It is 1, right?
Hmm.
So what is the predecessor of 1?
There's nothing.
No, 10 is the predecessor if you see here.
Oh, okay, yeah, okay.
So I found the predecessor, 10, and definitely 10 won't have any right. And then I have linked 10's right node to 1. And then I move towards 2. So what is the predecessor of 2?
4.
Then I linked these two guys. Then I went for 4. What is the predecessor of 4?
5. Yeah.
Then I linked this guy. Then after 5, there is no left. So that means this is one action point I have to take. So I printed 5. From 5, now I have to go towards right. What is my current now? Current will become 4.
Mm-hmm.
From there, I will again try to find the predecessor. When I tried to find the predecessor, I found, while in the process of finding predecessor, I found myself only, which is 4. Because I will go to 5, and to find the predecessor, I will go towards its right. And on the right side, I found myself. That means I did this part earlier also. Otherwise, there won't be any link of this if I would be doing this for the first time. So this is the most important thing. If it is not clear, then I won't be able to continue further.
Asim, you're saying predecessor when you're going down from 1 to 2 to 4. Isn't it going to be like a successor? I mean, like you said, we find 10, and then 10 is like, it's, how is it? So when you're linking 10 to 1, you're saying 10 is the predecessor
Of 1.
I thought 10 was the successor. I'm actually confused what you're saying when you say predecessor and successor. How do you find out what a predecessor is, and how do you link it?
So that's a good question. Thank you for bringing this up. So this is in order, right?
Correct.
So in order, if I have to ask what is the predecessor of 1, if I have to just point here and ask what is the predecessor of 1?
5. Sorry, 10.
Don't think in a way how we will find it in the code. Just think in that way. What is the predecessor of 1? Looking at this in order path.
5 to 10, all are predecessors of 1, right? But 10 is probably the most recent predecessor, or I don't know, the closest one or something like that.
Let's say, okay, let's say this is what is the closest predecessor of 1? The most closest.
10.
Okay. And what is the most closest successor of 1?
5.
Okay. So this is so this we agree that, okay, so now the algorithm says link the predecessor to the whatever find your current node. What is your current node? Link your predecessor with that node. So to find the predecessor of 1 or the current node which we are right now is go towards its right and then go towards its right, go towards its left and then keep on going towards it right till you're able to find the rightmost node. So if there are more things here, I would have gone more down. To find the predecessor, this is the algorithm. You go towards its left and then go towards its right. And now 12 is the predecessor. But in our case, our right side stops at 10. So 10 is the predecessor.
Okay. So this predecessor concept comes from the binary search tree, right? Where we're trying to say that, to the left is lesser than the current node and the right is greater. But the immediate predecessor will be go to the left and go to the extreme right of that node to get the predecessor. I think that is where it comes from.
Yeah. So if it is a binary search tree, the Inorder would be a sorted one.
Correct.
And then you would have seen the left side would be my smallest guy, and the right would be my big like greater than me, and that would be my predecessor, and that would be my successor. But the concept is same.
Correct. So you will have a function separately for a predecessor, and you do that for every node that you are trying to link back, or rather trying to find. For every node, you will be running the predecessor function separately.
Yes.
Okay.
So every time when I visit a node, I will try to find its predecessor. Right. So first time when I attempt 1, when I try to find the predecessor, I'll get 10, and I'll link it this guy. Correct.
Right.
Again, if I try to find the predecessor of 1, what will happen?
You'll just keep doing only that. You'll find, but
I will find myself only. So if you see,
oh, yeah, right. Makes sense. You come back to yourself. Yeah.
Right? Then I find myself only. So that means I did this path earlier. So that means in the past I did some action, because of that I got linked myself. That's meant now I don't have to do this thing again. That is the way to find I'm doing this the first time or the second time. So basically I'm finding the predecessor for the first time or the second time.
Okay.
That's the difference. So let's link that back again. So okay, so we link this and then we reached 5. So 5 does not have a left. So that is one action point. I can print 5 here.
Okay.
Then I'll go towards it right. Right, I will find 4. From 4, I'll again try to find the predecessor. What I found myself only.
Makes sense. Yes.
Then and now I have to also make my tree correct, because I can't leave the tree in a bad state. So what I'll do 2 things here. I'll remove this link, and I also print 4 here. So that means I am done. I have already covered the left tree. I don't need to do this again.
So to remove that link, you have already gone from 5 back to 4, right? So how will you again go back and remove the link from 5?
Because I will keep 5 in my temp.
Okay. Okay.
I'll keep a way of keeping the last right child or thing I visited in a temp. So there I'll just remove. When I'll show the code, you will be able to visualize it.
Sure.
So
Thank you. Thank you. Yeah.
From 4, I will go towards its right. Right is 2. From there, if I try to find a predecessor, what I find, I will find myself only. From 2, if I try to find the predecessor, I will find 2 only. So that means I can remove this link and bring 2 here. From 2, I'll go towards its right, 10. So at 10, there is no left child. So I can print 10. And from there, I'll go towards its right, which is 1. From 1, if I try to find the predecessor, I'll find myself only. So I'll remove this link and print 1 here. And then go towards its right, which is 3. From 3, if I have to find the predecessor, I'll get 5. I'll link this guy, go towards its left, 5. From there, I again try to go towards its left, there's nothing. I print 5 and make my current as 5's right, which is 3. From 3 again, if I try to find the predecessor, I'll get 3 only. I can remove this link, print 3. And from there, now I have to go towards its right, which is 6. 6, if I try to find the predecessor, there's no predecessor. And then there's no left also, and then I can print 6. So then I'm done with my in-order traversal.
Is the predecessor of 6 is 3?
No. Oh, sorry. Yeah. Predecessor of 6 is 3. But if I try to find this, let's see. Or I missed something. Looks like
But 6 is a successor of 3, right? It's not a predecessor.
yeah. But question is, when I'm at 6, if I try to find predecessor, what will happen?
So if you want to find a predecessor of 6, you will not find anything. It will be null, right?
Because there is no way to go towards its right.
Yeah, and then this will be the termination of the loop, the
Yes.
main loop.
Yes. Yes, so there I can't find a predecessor because there's no way for me to go towards right and go towards the left. So technically speaking, at every point I will not able to find the predecessor. This is only when I'm going from my current and moving down. I can show the code and then probably we can move forward because otherwise we'll lose really. This is really tricky. So I have to also look a couple of times to understand myself. Okay, so this is a code. We'll start the current with our root. And so this is the first point where I will say like, if there is current left is null, then put that in my result and then go make the current equal to current dot right. Otherwise, this is a step what I was telling. So when I was at 1, I'll try to go towards its right. So I'll take its left and then keep on try to go towards its right, or until I find myself only. So this is the first action point. If the right was null, this is condition I couldn't find myself. Then I'll make temp dot right equal to current, which was the link between the predecessor, and then current will become current dot left. Otherwise, this is a point where I found myself only. I'll put that in the result, remove the link, and then move towards its right. I will say like just try this out if you are interested in the solution. I think if in the interview you can give a stack solution, but if there is a follow-up, it's just you can just explain. No, I don't think like interviewer will expect you to code it there.
Yeah, it'll become a bit complex.
Yeah, it's just to give an idea like, hey, I know about this. Now, if you see the issue with this solution is we are redoing the same things again and again. So if you remember, we again go back to its parent or like, and again redo the same path. So although it is saving the memory, but if you see the computation will increase.
Yep, but really
Do you have an
interesting.
idea of the time complexity for this, Asim?
Yeah, it depends how your tree looks like.
Okay.
So worst case should be skewed only, no, like left skewed or right skewed, because that's a balance which you were drawing, right? That's the best proper tree what you were drawing.
It would be n square. If you have seen not n square, it would be.
But I think every node you are visiting 2 times at max. Worst case you can visit it more than that also. So n into 2, it should be order of n only.
Yeah. Worst case will any node twice on.
2 or more than 2 you are visiting anywhere. I don't think so.
No, the log n will come because of trying to find the predecessor, right? So that will have a log n operation.
Yeah.
So, and I think you're doing the predecessor like twice because you are trying to come back to yourself also.
Yes.
So I don't know how that will account for the whole.
Then for every element it will be log n into log n or what?
N
nodes will
log
be
n,
there.
yeah. And log n will happen 2 times, I think. So for each element,
Then
I don't know.
No, but the whole point is if you are visiting every node once or twice, right?
Twice, I think. Twice.
So it doesn't matter how you do it, but if you're traveling twice, if you're touching every node twice, then I think it should be O of n.
Yeah, otherwise it's not a good solution compared to the first one.
No. It's not about the good solution. I think it's about O of n then, because you visited every node twice.
How can you say that specifically for a predecessor? I mean, that function we are not sure, right? I mean, or will it? Or probably I'm missing something.
At least in the example, whatever he has explained to us, it looks like every node is traversed only twice.
Okay.
Yeah, it's trying
like based on the algorithm he explained. If the algorithm is wrong, then there's something else. But based on the algorithm he explained, this should be O of n.
But each time he traveled, that we revisit that node, that can be log n again, right? So he looked for the predecessor, which is log n.
No,
every node potentially will look for that. Wouldn't that be n log n?
But then what is the use of using this one?
Okay. Okay.
Okay, I'm also not sure what would be its, but because we have this while loop inside, which is also running.
I think if you click on the solution section, they might show you if solution is there. Only iterative.
This stack, and this is Morris Traversal, yeah.
Go below.
But their implementation is slightly different than what he has shown.
No.
Yeah.
It should be same because
your while pre-write is not null, you are using temp write also, right?
And log in intuitively complex.
Yeah, their implementation.
They're slightly different, yeah. So this is much better to understand yours.
But overall, they are also claiming it would be order of n.
And the complexity they are saying intuitively is O n log n.
Theoretically, that might be n log n, but
what do you mean by theoretically?
Like, I mean, you have some algorithms in which if you apply some maths, you might get some, like, let's say time complexity as X, but when you try to implement that, you may not be able to implement. There are problems like NP hard and NP normal NP, right? And NP hard and N problems, right? For them, theoretical, you have proof for that, but you can't implement such algorithms. So I mean, I'm not sure, just I'm guessing, like, could be.
Okay, so somebody has mentioned like this algorithm. So this is somebody has put something similar to me. He told here we are also recovering the tree, but here we are not recovering the tree. Seems like that's what this guy has mentioned.
So there is slight change there. Yeah.
Okay, I think we are really
Yeah,
over.
no problem.
So I'll probably hand over it to Shashank now.
Yeah, sure.
Yeah, thanks, Azim.
Okay.
Yeah, thanks.
Yeah, good explanation. The picture help a lot.
Yeah, that was. Yeah, we can go with the second problem then. So the problems is we are given a sorted integer array without duplicates. We need to return the summary of its ranges. Like the array is given to us 0, 1, 2, 2, 4, 5, 7. 0 to 2 since they are consecutive. So from 0 to 2 they have one range. Then 4 to 5 both are consecutive, 4 to 5 and 7 alone like here. So these are the 0, 1 and 2 form a continuous range and 4 and 5 another continuous range. And the same in this example, 0 and 2 are not continuous, so alone 0 is a range. I mean, again 2, 3, 4 continuous, so 2 is the starting and 4 ending, and 6 alone because 6 and 8 are not consecutive, and 8 and 9, so 8 to 9 they have given. So any approach or anything, any doubt? I think it's simple question.
So the input is always sorted.
Yeah, input is always sorted.
Oh, yeah, they have mentioned that.
Yeah,
Okay.
they have mentioned that indeed, and they won't have any duplicate.
Mm-hmm.
This should be an easy one.
I think it's just a two-pointer approach.
Yeah, that's fine. It's nothing, just we have to check if they are consecutive, just take the first and last and make it. If it is single, then they're two-pointer approach.
I'm surprised this they mark at medium.
Yeah, it should have been in. No, but implementing it will be a bit.
Yeah, tricky because
just some corner case. Yeah, corner
Exactly.
case. Yeah, makes sense. Yep. Yeah.
So two pointer, you are saying you are going to take both pointers from the same side.
Oh yes.
Okay, both starting from the left, or yeah, and then keep going, or maybe start from the right, either of it.
It says that's consecutive, so you just need to check that as soon as you find a gap. So put that in your output and change the pointer position.
Mm-hmm.
Yeah, I think I have also used the. So I took 2 pointer, one left, which I made to the initial, and right I'll be running over the loop. This is the corner case where I'll be checking if right reaches the end, or whether they are consecutive or not. And if they are consecutive, if there is only one element in the array, then we don't need to put this arrow. Simply you append it, or else you get the when you get the range, just put this arrow and then increase the left. Just append it and return. Any queries in this?
So you're just running through each and every element and then looking at them, and just trying to find if they are consecutive. If they are consecutive, just moving on. If they are not, then you are going inside the if condition, right? And then looking for if the left and right are same, then appending it, or else putting that arrow. Okay.
Put arrow, yeah, and then just increase the left after that by right, because till that time right would have reached to some other position, so left would be updated by the 1 plus right.
Mm-hmm.
And I think it will be order of n only, because we are going through the entire length of the array, this right pointer.
Yeah.
So any queries here?
I think, yeah, that's okay.
Okay.
We
Okay.
can
Let's
go.
proceed. Okay.
Yeah, someone has some question. Yeah, Jesh
Yeah,
was
okay.
talking, I think.
No, they're telling like go ahead. I think. Okay, let's move ahead. So this count, you have to count of smaller numbers after self. We are given an array of integers and we need to return a new count array. The count array has a property where count of I is the number of smaller elements to the right of nums of I. So what they're telling is like we'll be given an array of numbers, and to the right, like one's right, you don't have anything, 0. To the 6, you have only one element which is less than 6, so 1. To the right of 2, you have only one element, 1, which is less than 2, so 1. And to the right of 5, you have only two elements, 2 and 1, which are lesser than 5, so we are appending here 2. So question is clear, I think. So any approach in this?
So for every element, look at the other string, the whole string, to its right side, and then only find whatever the least number of elements are compared with this value. Right? That is what it says. Okay, just keep on counting them.
Order of n square it will, right? For every element, you'll go to the right and check which is smaller.
Yeah.
Yeah, so it will be n square or, yeah, it is n square, yeah.
So can it be optimized further?
I just tried the optimized version of that brute force using the set and the low multi-set actually in C++ and the lower bound, and enumeration start from the back and just checking that if there is any element on the left hand side of that. But that's again the worst case is actually the n square.
So what will be the optimized version?
Optimized one, like binary search, we can use it. I think let's
binary search.
BST.
But this is not a sorted one, right?
It's a it's not a sorted one, but we can. Okay, I'll show you. I think with then it'll be clear. So the print screen is visible. No, it's visible.
Yeah.
Okay. So let's. I think the array is 5261. So what we'll do, we'll start here from the back. So let's. Where is the arrow? Yeah. Okay. Let's start it. Let's say first element is 1, right? So from the back we are starting, and let's keep a count for them as 1. You'll come to know why I've taken count. Count will basically give you how many elements are to the left of it.
Yeah.
Okay, for 5 1 we took. Next element is 6 for us. Now we'll first compare whether 6 is greater than 1 or not. So 6 is greater than 1.
And could we put the example there, the array sample?
Okay, sure. I think you can put it. It's 5 2 6 6 1. Yeah. Okay. So we have this node. In node, I'll take the value of the node and the count. So count will basically tell you what is how many elements are to the left of it. We will get the clarity for the count as we go further. Now let's look for the 6. If you see 6 is greater than 1. So definitely to the left of, to the right of 6, there is a number smaller, which is smaller than 6, which is 1. And so let's put 6, 1 is greater, 6 is greater than 1. So let's put 6 to the right of it, I think. So makes sense. Like, let's put here, if you put here 6, and let's keep count for this as 1 again. You'll come to know. Now let's come to second. If you compare second with first, so for 6 you got element as 1. There is one element which is smaller than 6 on the right side. Now let's come to the 2. 2 is bigger than 1, and if you 2 is bigger than 1, so one element is smaller than 2, that is 1. So this count will give you value of 1, and so we'll go here, and here we'll check whether 2 is greater than 6 or not. 2 is not greater than 6, it is lesser than 6, so it should go to the left of this. So it will be, if we keep here, so this will be this will be 2, and for this the count is 1, and for this we'll increase the count for 6 to 2 because one element is smaller than 6. So I think, okay, let's update it to 2. It's 2 actually. Okay, let's remember the updated value is 2. Now let's look for the 5. So for the 2, what you can say, the elements which are less than, we compared here 2 was less than 1, so we'll return the value of that node from that count value will return from that node. So for 2 we'll have 1. Now let's look at 5. 5 is greater than 1. Okay, so count 1, this count you can take as 1. Again you'll go here and we'll check whether 5 is greater than 6, but it's not greater than 6. Now let's come here. 2 is greater than 5 here, that's true. Since 5 is less than 6, so you increase the value of 6 by 3, and 2 is greater than 5. So let me draw this tree first.
The 2 is smaller, yeah, okay.
So you can go here, and so this is, you can keep 5 here, and count will be 1 for this, and your count will be 1 for this. So now you can see, now let's go from the beginning. One we draw like this, we went for the 6. 6 was greater than this 1. So we'll return the value of the count from this node. Now again we go for 2, we'll check whether 2 is greater than 1. That's true. So we'll take a variable, any variable, add count this value 1. Again this 2 is not greater than 6. So we'll go to the left and we'll put here. Now go for the 5. If you go for the 5, 5 is greater than 1. So take this count. 5 is not greater than 6. 5 is greater than 2. So take this count. 1 plus 1, 2. And now there is no other element, so you put 5 here. So for 5 you got 2. So for 5, 2 elements are smaller. Now if you take 7, let's say I had 7 here. If I have 7, for 7 is greater than 1. So count value will be 1. Then 7 is greater than 6. Okay. So when 7 is greater than 6, count's updated value is 3. So 3 plus 1, 4. So if you have 7, there will be 4 elements which are to the right of 7.
Okay, got it.
Yeah. Any queries in this example, like any step? Whenever you find that your value is less than the given node, you increase the value of that node by 1. Initially 6 was greater than 1. Yeah. So now 2 is less than 6. So I made 1 to 2. Now again 5 is again less than 6. So I made it to 3. What this helps you, what this count will give you, when you encounter any number greater than 6, it will give you value of all the nodes which are less than 6.
Okay, but in this case you are trying to create a binary tree first.
BST, huh? I'll be creating it and then updating the values.
Okay.
It should be a normal BST or self-balanced. I believe it should be balanced.
Yeah, if balanced, I think for that you have to use AVL and all.
It is not balanced, it is just binary search tree.
This is a binary search tree, but we can, if we want to use balanced one like Fenwick tree or AVL tree, I think we have to use for that. That
but
can
if
also
it's not, if it's not balanced, then the complexity will be same like.
Yeah, that will be a problem. Yeah, but it won't be. I think order of n square won't go to that.
It's order of n, right?
Because worst case, what you'll have, you can have either all the elements to the right of 1 or right of or left of 1.
But if for every node, you always look at the you cannot skip it. You always look at the leaf, the node, and that would be n square.
For
so
unbalanced,
let's say you got 7. For 7, what you're saying, we don't need to go.
Yeah, but in the worst case, you cannot stop at 6. You have to stop at the leaf node. Then that would be n square then.
Yeah, to get that log n should be, balanced tree.
But what if there are some duplicate nodes with the same value?
Yeah, you can create one more variable here, duplicate variable. You are saying regarding duplicates, right? I mean, value having equal to 1, right? Yeah. You can, in that case, you can maintain one more variable and just add count plus dup. I've taken that case in the code. Or we can go, the other approach is like we can go with the merge sort also here.
Like, but in this case, the worst case will be n square, but average will be n log n something, right? Or maybe even n.
If it is n square, like every time I have to, in the worst case, I have to visit to the leaf, right?
But that will be only in the worst case. So
yeah.
It is much better than the brute force where it was going to be always n square.
N square, yeah. But here at times could be like n log n or less than.
But this one also need to build a tree, right? So need extra space.
Extra space,
Yeah. So at the cost of space, we are reducing some time.
Yeah, but even if you do sorting, you will still need a space. Because you'll have to get one array. You'll have to construct an array. Yeah, you can do it in place too. But doing in place during an interview for a different, it might not be so easy.
Okay, let's look for the second one, like merge sort. That also, if we can, like, let's see. So for merge sort is like, let's say element is 5, 2, 6, 1. So we'll take the mid of it first. So 5 and 2 would be one side and 6 and 1 would be another. Then you'll have 5 separate, then 2. You can have 6 and then 1. So here the concept is like, main concept is in merging. When you merge 2 and 5, left is sorted and your right is sorted. If you see that this 2 is smaller than 5, so definitely one element is there which is less than 5. So corresponding to 5, you can get, let's say, yeah, 5, 2, 6, 1. So here you can have 1 because these two, I mean, 2 is lesser than 5. So one element to the right of 2 will be less. Now when you merge it, it will be 2, 5. Oh, sorry. I think it will be clear in the next step more. This is 2, this is 5. Now let's go for the 6. Now 6 is again smaller than, sorry, 1 is again smaller than 6. So you'll have one element which is lesser than 6 on the right side. So corresponding to 6, we can give 1. And this will turn out to be 1 and 6. Now we need to merge these two arrays. Now let's see, we'll check 1 is less than 2. So you now left is sorted, right is sorted. Since 1 is less than 2, that is the minimum of the left element, and you are is even from that this 1 is less. Definitely this 1 will also be less than 5 because of this sorted array you are picking the minimum element 2, and 1 is even less than that. Then definitely it will be less than 5 also. So for 5, you can increase it by 1, and to 2, you can give 1. So now the pointer will go to 6. Now coming to 6, 6 is greater than 2. So definitely we can't increase. Definitely there will be no element greater than, there will be no element smaller than 2 on the right side. Now we'll come to 5. 6. So your pointer reached to 6. Now if you check this 5 is 6 is again greater than 5. So corresponding to 5 also, we won't have any greater element on the right, smaller element on the right side. So this will be like 1, 2, 5, 6, and we'll get 2, 1, 1, and for 1 we'll have 0, 0 up there. So here any queries in this one explanation, like where?
What is the time complexity? I think beside n log n, but like in case of, like on line number 52, we still need to look through, 2 to 5, right?
Yeah.
So we see one way to look through to 5 to update it. So would that be additional?
Extra space you're telling, or time for?
I think the space, only extra space will, but the complexity
Yeah, space
will
it
not
will
increase.
take, because divide and conquer you are following. So
yeah,
that will have extra space.
Yeah, but normally, like when we do the merge sort, we only look at one element at a time. But in this case on line 52, you look at 1 and 2, 5, and then we have to look through that array, right? 2, 5, and then to update the value.
No, I'll take here I missed the index. I'll take element along with their index. I'll take an index array. Like 5 will be at 0th position, and 2 I'll take, 2 will be with 1, 6 will be with 2, and 1, 6 will be with 2, and 1 will be with 3. Along with the index, we'll pass the element. Like 5, 0, 2, 1 pair of element along with their indices. So that we don't need to look back. We'll only update the index. We'll update the value at their index point.
Okay. So suppose on line 52, that's, instead of 2, 5, we have like a lot of element on that, left sub array, right? Then we have to look through each one of them, right? To update it.
Yeah.
So that would increase the time complexity or no?
No, but that you do for the merge sort also.
Merge
right?
sort also you are doing, huh?
So you are using the same thing.
Oh, is it? Okay.
Yeah, you're just comparing. You don't need to do the extra step here.
Yeah, there's nothing extra there, I think. Yeah.
I think it will be order of m plus and this space, and whichever array is having the larger length, that would be the extra time, order of m or order of n here at line 52, like for merging that. Worst case, let's say left, all the elements of left are smaller than all the elements of right. And let's take a case in which now let's say that all the elements, the first element of this left array is greater than all the elements of the right. So the pointer will go to the end of the right array, and let's say right array length was n by 2. So for merging, because once the array, this array gets finished, this is already sorted, we'll append it directly. So it will be order of m, order of n, whatever it is. I mean, the larger the length, whatever the length will be, that will be the time complexity for merging these two.
I think like what he's saying is, like if you're going to like merge that in 52, 1 goes to place 1, so that means 2, 5, 7 everything has an element lesser than on the right side. So we need to update 2, 5, 7. In MedSort we generally inserted it in MedSort we generally inserted at position 0, but here we need to do something extra. We need to visit 2, 5, 7 and update their counts. So that's an extra complexity we had.
But they have told they have told here that you can use a count array. So we are not using any extra space. According to the problem, they have already told here you can use a new count array to return.
No, I'm talking about not space, but time.
Time, yeah, I think for update, definitely.
We are
Because
taking more time than n log n.
let's say here 2578 is there, 1 is smaller than 2, then for all 2578 you have to update it by 1. Your order of, so but you will take the upper value only, no?
So
If
the
it
way
comes order
he's
of n
saying,
plus order.
whenever he's comparing, actually, so he might be maintaining some sort of a counter. And so whenever you come to that particular element, you will just update that counter value into the count array. So that might not be much of processing work there.
I think we can keep one extra variable like write counter.
Yeah,
and
something like
update
that,
it. Yeah, that would reduce the space.
Not only space, but everyone is concerned about the time,
Time.
So they are saying that merge sort, whatever you do, you are going to additional you'll have some more time you are going to use for processing for doing this step,
Updating the
many,
counts.
how many elements are before any element, so that is what it is. So maybe if you have a code you can walk through, that will be much.
But when we are merging, so we are just directly updating the count at that index position.
At the same time we are doing, it's not like.
Yeah, but everyone is saying, how are you going to get that count? So you are going to do some processing there, right?
Yeah, we here we know that when we are merging left and right, so whatever we have in the right array, so if it's a smaller the current element, so we know that we have to, that is on the right hand side, so we have to just go and update the count.
Yeah, exactly. So we are not going to do anything much here, but only just keep a count variable and keep on incrementing that count as and when we are seeing anything is lesser than that value, and then
So here what will happen, it will update the same index multiple times.
Yeah, might, for 5, like you can say.
Yep. So why don't you run through your code if you have?
Yeah, this is for the BST. I think I've done only for the BST that I haven't. So first I made a count array. I will till the length of a nums I fill them with 0. If you have only 2 numbers in your array, just return the smaller one. Only one. You have 2 numbers. If you have written the smaller one, then we are reversing the array from the backside. Took the root we have taken in the node. Now just we are checking if your value is less than node.val. Then just update. I have taken one extra this variable count, or smaller, what you can say. The smaller denotes how many elements are smaller to the left of that element. So as and when you find that it's smaller than the root, just update it. And if it doesn't have any left tree, then since the element is smaller, so it will go to the left side. So put them into left side and come out of the loop. And this is vice versa of that. Like this now you'll need to update that count. Whatever value you got for the count, whatever smaller value it was. I think there I use the count variable here. I'm using smaller. So whatever the value of smaller is, that just to add to the count value. And if it is greater than 1, like 6, we were comparing with 5. 5 was lesser than 6, so you have to update the value of 6 by 1. The count value in that by 1. So this is, and if you don't have any right child, then just update it and come out of the loop. At last, we'll update. For every element, we'll update this count and return the smaller. Here I'll update for this array, I'll update it.
So Sashank, this one, it treated like a tree, but visualized just like a linked list, right? Because at the end, each intermediate node only have one child.
Yeah,
right?
Kind of, yeah, similar to what, like in
And Shashank here, so if you have
Yeah, sure.
duplicates,
Yeah,
then
I haven't.
yeah, that's
I
fine.
think I
So
haven't.
you
Yeah. Okay.
that's okay. But I'm just trying to understand if you have duplicates, and so if you have two again, right, in that whole list, if you have two again, but before the two you have another number which is lesser than it, then
Yeah.
how do you ensure that for the subsequent? Oh, okay. So we just we update the count, and that count is what is taken. Is it okay? So the new
Taken.
count will
Yeah.
come with the new duplicate. Okay.
Duplicates. Yeah.
Okay. Okay. So we don't really have to maintain another variable like a duplicate. You mentioned we have to maintain another variable called duplicate, right? Is that required?
Optimize it by by removing that duplicate. Here I haven't taken care of that.
Okay. Okay.
I have. Yeah.
Okay. Thank you. Thank you.
Okay, yeah. Yeah. Any queries in this further?
You know, initially I read the problem statement. It looked like we can use the monotonic stack to do it. And have anyone tried that?
Monotonic stack. Like, could you explain a bit more?
Like before, like we look for the element smaller. Let's say we look for a smaller element on the left, on the right, right? But it counted only one. Like previous problem we do, we given an array and we look for any element, we look for the smallest. Look for smaller element on the right. So somehow this one, it you know.
If that only works, looks to me that if you have to find the first smallest element, but here you have to get the count.
But if I was thinking because it kind of like a linked list, right? Because this element, the first smaller one would be this one, and then the smaller one could have the smaller on the right. But I have to spend more time to think about it.
First, I thought like this, I could have gone like from simply scanning from left. For 1, let's take 0. Now, since 6 is greater than 1, so definitely we'll maintain, definitely this, it will be 1 for it. Sorry, 1 for this. Now, 2 is not greater than 6, so we will take the value of whatever the value of 6 is, same I'll continue to 1. Same I'll continue for the 2. But now, again, 5 is greater than 2, so I'll add +1 to the whatever value 2 is having. So it was 2, it will be 2, but I think it's fit only for the example this only. I started from the back. For 1, 0, 6 is greater than 1, so so 1 was having the value of 0, to that I added 1, so it became 1. Now 2 is less than 6, so I'll take the value whatever 6 is having. Now again 5 is greater than 2, so whatever value 2 is having, I'll update it. +1, I'll update to this value. So, but I don't, it won't work in, if let's say in other example I tried.
Maybe
because let's say if one more element is here, I don't think so it will work for.
Yeah, you can take that.
I think it won't work.
364. Yeah, you can take example 364.
Yeah.
364. Yeah. Let's say for 4 we have 0, and because 6 is greater than 4, so I'll add 1 here. Okay, I'll add 1 here, and now 3 is greater than 6. So I was saying that I'll take the same value whatever 6 is having, but that will become wrong here. I can't make it 1 here. Otherwise, it would have been odd often, but it won't. can't we use tag and
So you said you haven't implemented the merge sort?
Yeah, merge I haven't implemented.
Okay, if you want, I can quickly run through. If
Sure. Okay, I'll stop my share. Yeah, you can share it.
Okay. Okay, so my screen is visible, right?
Yeah, sure.
And I think, yeah. So we start from here. This is the entry function. So
Okay.
I'm maintaining two, what do you say, arrays, one for num and one for the indexes. Okay. So
Yeah.
this is the indexes and this is the value. I'm just copying the value again over here. I think, yeah, I'm not sure whether it is required or not, but I'm using that. And then I'm what do you say, populating this IDX, which is the index values.
Okay.
And this is the merge sort. So merge sort is having the first parameter as the same values, which is our nums, and then the indexes, and then this is the left and the right. So, and this is the count, which I'll be returning, the count array. Okay. So this is a normal merge sort. I look for if the left is greater than or equal to right, then return it, or else I find a mid position and then I do a merge sort of the left to m, and then m plus 1 to r. Okay, so this is a normal merge sort. And then this is the merge actually function where I take in the values, which is the nums, and then this is the indexes. And I have 4 variables for L and M of the first one. Okay, and then the M plus 1 and R as the second one, and then this is a count. And so the merge is the only function that's slightly complex.
Yeah, this one.
Yeah. So here actually what I'm doing is I'm creating two arrays to copy the values and indexes again. So from so I just calculate how much what is the space I'm going to need. So by using the end of the my right one and the start of my left one, and then I get a count.
Last minus first.
Yeah. So I just update these two values of the arrays over here. Okay. Okay. So first I don't update, but when I'm going through a while loop, okay, whenever I go through while loop, I look for when I'm just setting this low pointer, which is the left side pointer, and this is the high pointer, which is the right side pointer to the initialized position of both these arrays. And then I compare their values first. So whenever is the left side is lesser than the value of high side. So this is one variable which I am taking, as you discussed earlier, is the right counter. And that's the only variable I'll be incrementing whenever I find any value from the high side is greater than this one, So then only I'm going to increment, or if it is less, then I just set this variable to my counts array. So that is the only extra thing is being done over here. So if you look at it here, if I compare my left side value, if it is less than or equal to high, so it means this is the time when I can actually put my right counter, whatever I've incremented earlier, into this count, and that will be my count value. So I'm just counting over here how much times how many variables or how many elements are smaller to my right side, which is the higher one. So whichever is the higher one. So I'm just counting it here, and then I'm assigning that to this count variable. So the counts array. And
so right
I
counter
get the index through this index array. So I need this index array. That is the only reason I need index array, or else I don't need it. Sorry, go ahead.
So for every next iteration, right counter would be initialized to 0, or it will keep the.
So every, in the sense, because this is a merge sort, right? So you come to the very end when you have both the right and left least, both of the
Single.
vectors as, yeah. So whenever you come, it is going to be only initialized once.
Okay.
So when because
yeah.
both of them are being always sorted when you come over here.
Yeah.
So you need to just compare with those two.
Okay.
So just do for these two, and then whenever you have whatever is left over, just assign those variables in this count variable, and then that's all. There's nothing much to do there.
So you'll be passing element with their indices or simply element? I think you're passing the indices.
Yeah, I have to pass the indexes. You know, if I don't pass, then I won't be able to actually enter that
Update
index
it.
value. So I have to take that index value over here, you know, to find where in my counts array I need to store that value. It's slightly tricky to understand that, but it's not that complex once you go through it once or a couple of times. So it's easy to understand this, and it's much easier to remember also. Yeah, that is what I thought.
Because it's similar to merge sort only, slide bus.
It is merge sort, yeah. It's only this counter portion. This is slightly different. That's the only thing which is slightly peculiar about this one. And then again, you have to maintain an index array.
Yeah.
So because you don't want to lose the position.
Yeah.
These are the only two things which are slightly different in this merge sort. Yeah.
And there won't be any extra space also because they themselves are telling to return it in a new count array, right?
But still, that will be counted anyway, right?
See, space is what when other than program, what extra space we need, that is considered as the extra space, right?
Yeah, but we again, I'm using one array for indexes, so that is also extra.
Okay.
Yeah.
Okay. Yeah.
No problem. Thank you.
Yes. Yeah. Thanks. I think stop the